of you might want to come back and watch this, because it's just intriguing. And actually, some of you are leaving early for swim Sunday. So, an object moves along a straight horizontal line so that at any time t, from 0 to 9, its position is given by this equation. So, if our question says what's the velocity of the particle at t equals 5, is it moving to the left or the right? Okay. So to find velocity, what have we got to do with our position function? Take the derivative. So this is what I strongly prefer. I need to go look through the Facebook group to see if anybody's answered this question, and if not, maybe ask it. So when you take the derivative of this, here's what I prefer for you to do. Say x prime of t equals v of t, and then v being velocity, and then just take your derivative, so negative 3 plus 2t. So in this case, you need to try really hard to stick with the t, because they're calling this x of t, so if you switch your t to an x, it could look confusing, because x is already in the problem. If they use an s instead, you can get by with it. They won't really care that much as long. But if x is already somewhere else in the problem, you don't want to do that, because it could cause you trouble. So I like labeling this as x prime, then calling it v, which stands for velocity. I think you can get by. I know for sure you could probably get by without saying v of t. I think you're probably going to be okay if you just go straight to v of t. I think they will assume that you mean velocity whenever you do that, but I'm not 100% sure about that. So that's why I like for you to put both. I'll go check with the Facebook group to see if anybody's put anything about that. So, no, once you have, just once, and then you have shown that x prime is v, and then you could just use v from there on out if you want. So definitely don't do it the whole time. But this lets the grader without a doubt know you knew to take the derivative of x, and that was the velocity here. So I like this notation here. It just clears it up so there's no doubt that you knew what you were doing. And so if we want to know this at 5, we just plug in 5. So make sure you label this v of 5. So negative 3 plus 2 times 5 is going to be negative 3 plus 10. So we will get 7. Now, it asks about it moving to the left or the right. It is going to be right. Why is it right? Positive. You guys have had enough physics to know that, right? So we'll say since.
Maybe collectively the physics class got
Yeah, I don't even know why we put that class.
Since v of 5 is greater than 0 or is positive, the particle moves to the right. That's fine. You can do that. Okay? Alright. What is the acceleration of the particle at t equals 5? Is the particle speeding up or slowing down? This is, you need to pay attention to, because to me this is confusing. So, it asks for acceleration, so we need to find the acceleration. At this point, you could call this x double prime or v prime, or whatever. I'm going to call it v prime of t, but if you call it x double prime, either way, you've already established that v is the derivative of x. Now we're saying that this is the derivative of v, or you could just say x double prime. It doesn't matter. You're showing a chain of derivatives here. And I'm going to call it A of t. I just prefer to have v and a because it makes it really clear if you're talking about velocity and acceleration. And so if I take this derivative, what am I going to get? Just 2. All right. Now, we need to know whether the particle is speeding up or slowing down. Did you learn it is speeding up in this case? Did you do this in physics to be able to tell if it's speeding up? Okay, what is positive?
Acceleration. The derivative. Yeah.
Okay, acceleration is not the only thing you look at for speed. Yeah. So, if our velocity was negative, but our acceleration was positive, you'd actually be slowing down. Okay? If you're, so if velocity is negative, but your acceleration is positive, then you're actually slowing down. So the really easy way to remember this, and I'll write this down here for you, if v of 5 and a of 5 have the same sign, the particle speeds up. Okay, so either they're both positive or they're both negative. The particle is speeding up. Okay? Right, because if they're both negative, if you think of it like as left and right, even though it's so hard for me to sort of think about this. If you're positive, it's easy. If you are moving in the positive direction and you're also having a positive acceleration, that means you're speeding up. Well, if you have a negative velocity, that means you're moving in the negative direction. So a negative acceleration means you're moving faster in that negative direction. So same sign, speeding up. If you have different signs, so if v of 5 and a of 5, yeah, you could put v of t. It just has to be like at the same point for you to be talking about it. So like you wouldn't compare v of 5 and a of 3. That wouldn't make sense to do.
So it like has to be the same number.
Yeah. Yeah, because you're talking about one singular point. Yeah.
It's the same number.
Right. Have different signs.
Would we ever put in another number in besides the same number when we do the change?
No. The particle slows down.
So it doesn't matter which has a negative?
Correct. So it could be positive velocity and negative acceleration, which makes sense to us, right? Because you're going in the positive direction, and you have a negative acceleration, which means you're slowing down. The one that really makes my mind want to explode is you're going in negative direction with positive acceleration, which means you're still going in the negative direction, but you're actually slowing down because acceleration is positive. But that just hurts my mind to even think about what's happening there.
It's pushing the number to 0.
I guessed. Oh, gracious. What's Siri want to know about this? She is trying to tell me how acceleration can be negative, actually.
Oh, really?
Yeah. She's trying to help me out here. But it is also perfectly acceptable to just know this rule, which is what I default to most of the time, instead of trying to picture what's happening here. You may be better at picturing that than myself, but if they have the same sign, you're speeding up. If they have different signs, they're slowing down. You have to consider velocity and acceleration. What most students do wrong is they just look at acceleration. If it's positive, they say it's speeding up. If it's negative, they say it's slowing down, which might be correct. Like that would be a correct assumption in this case because velocity is positive, but you won't get the point for explaining it if you don't talk about acceleration and velocity. So we would say here the particle speeds up.
Position does not play a role in determining.
Correct.
Unless, except getting velocity.
Right. You have to have it to get these two, but it does not determine anything about speeding up or slowing down.
And then, of course, we jump right to the He's like 2.1 in it. 2.2.
So you could say they have the same sign. You can say they're both positive. You can word it different ways, but you have to consider velocity and acceleration.
What is actually the purpose of
E is crazy and can be used in so many different situations. Like its primary application is that it's used in like continuous growth. So like it might be like the growth of bacteria in a petri dish, or it might be like population growth or something like that. It shows up like a lot. It best models like natural phenomenon that you see. But it is just a constant, and then like it just shows up in other stuff that you don't even think should be related to it.
It's just a number that repeats a lot in the world.
Yeah. Yeah. It's a lot like pi. Pi is a lot easier to understand where it comes from, because pi is just the circumference divided by the diameter. But E comes from the situation of exponential growth, but it shows up in places that don't really have anything to do with exponential growth sometimes, which is crazy to me. Yeah. Euler. It looks like Euler, but it is Euler. Just wait till later, in a week or two, when we learn about L'Hopital's rule. L'Hopital. Some people call it L'Hopital. Joe Gallion liked to call it El Hospital. In his defense, some people spell it with S, and it does look just like hospital. But those of you that love spelling are really going to love him. All right, so we've got this equation. It gives the position on a straight line at time t, and this is calculator active. Should put a calculator here. So find the times for 0 to 20 at which the particle is at rest. So we definitely need our calculator, not this one though, because it's weak. Yes. Yes, I am recording, so my swimmers, I will post this after class. You guys need to go. Good luck.
So is this, you just comment with the velocity?
You're so funny. All right. Go to y equals. Oh wait, let me give you guys.
We don't need to over.
I mean, it's okay.
Nothing. I didn't do anything. I was in a free parkour accident.
What did you do?
I didn't do anything.
Margaret?
I jumped off the bed and I why are you telling me to do that?
All right. Okay, we We do not have much time. We need to do this problem. All right. So, we need to find when the particle is at rest. So, how can we tell when the particle is at rest? Yes.
Yeah, well, I mean, so since it's as long as it's decreasing, you can get to that point when it's decreasing. You find when the derivative.
We want to know derivative. No, because if we take the derivative, that gives us velocity. What is your velocity if you are at rest? It is 0. So we're going to find the derivative. So F3 derivative. I've got mine in y equals, so I'm going to do y1 of x, comma x.
Wait, differentiate?
Yeah, differentiate, yeah. F3, and then to type in y1, you just type a y and a 1. It's not a special button.
Have you put solve outside of that? You can go ahead and send it.
Probably so. Probably. I'm gonna copy and paste just so we don't have quite as many parentheses in there, but you could probably do that.
So you put into y equals.
Right, I put my equation into y equals so that
Type in y1.
right, just type a y and a 1 of x and then your comma x. And so when you type this in, it's going to give you the derivative. This is not one that we can easily find by hand. We could find it by hand, but not easily.
Could you do that thing with like therefore the line?
If we do that, that would plug in 0 to this derivative. So we don't want to plug in 0. We want to set this equal to 0. So since this is calculator active, you don't really have to show any work. You just want to show that you're putting f prime of x equal to 0. And then we can solve that using the calculator. I think Daniel said that he got it to work where you just do solve and then do this like derivative and do the whole thing together. So we don't have so many parentheses. I am going to do solve, which is under F2. And I'm going to pick solve, which is number 1. And I'm going to go up here and just highlight this and hit enter. And I've got to put equals 0, comma, x, and close my parentheses. So we do solve, go up there and copy this and put it down here, equals 0, and then comma x. And telling us more solutions may exist. And we are getting x, oh, gracious me. All right. We're getting x equals 10.6386. Huh. We got 0.02085. It probably is this where this is like a, I think it might be kind of like a knockoff thing. So they told me that like technically you're supposed to have an actual TI-89 to download this. I'm not sure. It seems a little. I did nothing because these computers are under like deep freeze. I can't even go to my settings and change stuff. So if anything's wrong with it, it's Ricky or Scotty that did it.
I saw Scotty today. I returned my computer.
Yeah, this is a lot easier to write on.
No, this is from like last year.
Are you the only one like that?
Might be the only one with this brand. The they still have the smartboard ones, which actually worked a little better, but they quit making. Well, actually, the new ones that they make are like $30,000 plus you have to buy a membership to the smart notebook program that costs like so much per month. So they have started getting these off-brand ones that aren't perfect, but possibly worth it for the money. So they're good enough. Yeah. Yeah, that's right. There's nothing wrong with that. Good enough. All right, so what is the position of the particle at x equals 0?
Position of the graph.
So position, which equation should I use?
Just look at the space of the first,
The original? And I should just plug in 0. So it was called f. So I'm going to say f of 0, and here's the cool thing about this. This is why on FRQs I really encourage you to put the equation into y equals. Because I don't have to type this all in. I could just do y1 of 0 since my function is in y1. So it saves you a lot of time there. You just get 6. This is calculator active, yeah. So that's all you have to write. You don't have to write down any of the work where you actually plugged it in. You just have to make sure you label it f of 0 and write down 6. Now, you do need to put f of 0. I'm not sure you would get full credit if you don't put f of 0.
So just f of 0 equals 6, just like that?
Right.
Okay, so we don't have to put 0 in.
Right, you don't have to show where you plug 0 in. Because it's calculator active, they're assuming you're doing those things on the calculator. They don't need to see it. All right, position of the particle at x equals 20. F of 20, what do you guys get when you do that? 12.5435. Okay.
Oh, 6.5. What's the unit of measure?
Okay, here's the tricky thing here. It says what is the total distance that the particle traveled on the interval from 0 to 20. So, if I use this example, let's say that Daniel has to go to the bathroom and uses the bathroom pass because I'm not going to let him go unless he uses one. But he's desperate, he uses a bathroom pass. So, if... What did he say? Alright, so, if Daniel decides that he's going to go to the bathroom and uses bathroom pass, then Daniel, let's say he goes out this door, he goes down to this bathroom, and it's closed because they're cleaning the bathroom. So then he will turn around, and he will go back to this bathroom over here, use the bathroom, and come back to class. So, if we only look at how far he was from the classroom at 2 certain times, we're not going to get the full picture, right? We're just going to see maybe the distance from here to that bathroom. But his total distance was further because he went down here first, came back to where he started, then went this way and came back, right? So, it seems like you should just be able to subtract these two and get the distance that was traveled, but that's not the case, or not always the case. So, if we subtract 12.5435, if we take 12.5435 and subtract 6, what we're finding is the displacement, how far this was from whichever point we're talking about, right? So we find the displacement, but that doesn't necessarily tell us how far. Let's say I let Daniel go to the bathroom and he wanders around the school for 15 or 20 minutes, right? Goes and checks in with 3 or 4 different people, then eventually comes back, right? His displacement, I thought, was just from here to the bathroom. But his actual distance traveled could have been much, much, much further if he just wandered around for a while, right? So, it all depends on direction. Now, we're going to be dealing, like, actual bathroom, you know, there would be, like, if he wandered around, he might go upstairs, he's traveling in 3D. We're going to be just linear directions that we're talking about here, so it's going to be left or right. So this particle was either going left or right. So, if we graph the derivative, we can tell where this function is going to switch from going left to right. So, I'm going to go back to the main screen. My derivative was this right here. So, I'm going to copy that. So, just green button and that up arrow is going to copy. You got a couple options. You could either just go ahead and replace y1. We're pretty much done with it. Actually, no, we're not. No, we still need it. Don't get rid of y1. Put this in y2. Just paste it here. Green button and escape. And that's our derivative. We really only want to look at the derivative. We don't want to look at the original function. So if you go up here and I think, well, on the on the 84, you just have to y equals. See, I don't really want this to happen because I don't want it to graph both of these right here. We're running out of time too. And how do I get that check mark to go away? I can't remember. Anybody know? I thought you hit the arrow button, but that doesn't seem to work. F4?
Oh, maybe you can't be like that.
Let me go up. Okay, yeah, there's a check mark right here. So we want to go up here for F1. We want to do F4. That way it will not graph that original. It'll only graph the derivative because that's all we care about. It's probably bad. We really need to be from 0 to 20. So if I go to my window, actually I'm 0 to 30 right here. So I'm going to make it 0 to 20. This is what I typically do for zooming. I'll go ahead and change my x's to 0 to 20 because I know that's the window I'm looking at. Hit graph. You're probably still not going to be able to see it that well. You're just seeing like a little piece. Then if you do F2, which is zoom, and go down here to where it says zoom fit, it's going to automatically adjust your y values to where they're correct for those given x values. So, remember this is velocity.
Oh, wait.
So, if our velocity is negative up to this point, we are going to the, I think this one's going left and right. Correct. We're going to the left. Actually, it doesn't really tell us. Straight line. We just know it's a straight line. Let's think of it as left and right. You can either think of it left and right or up and down, right? Negative being left or down. So we're going left to here, but then we're going right for the rest of the time. So we need to figure out what this value is right here. And so we'll do F5, 0, lower bound, upper bound, and we get 10.6385. Okay, so we'll say F prime of, is it T or X in this one? X. We found the value of F at 0. And we're out of time.
Wait, I thought we already found that 0.
Not for this one.
Did we already find the 0? Yeah, we did. You have it up there.
Oh, maybe we did.
That's what I was thinking.
Oh, wait, how's there another one? Why is it not showing up? The stupid star test has messed up and me being off.